In this work, we propose a continuous flow maximization approach for the task of connectivity-driven parcellation of the brain's cortical surface. This is done in order to allow for brain connectivity analysis, which can provide essential information towards understanding the brain's organization, its behavior, and the impact of neurological diseases. There exist two main modalities for mapping the connectivity information in vivo. The first one is diffusion MRI, which can provide information on the structural connectivity of the brain, while resting state functional MRI allows to infer how the brain is connected functionally. However, the information we obtain at the voxel level has a very high dimensionality, which makes direct network analysis impossible at this scale. What is typically done is to parcellate the brain into a set of cortical subregions, while each subregion will correspond to a node in the connectivity network. This allows to build much lower dimensionality networks that are tractable for further connectivity analysis. Most connectivity studies use random or chiral parcellation to build their connectivity networks. However, this can lead to a loss of information and a bias in the way the network is constructed. Using connectivity-driven parcellations allow a much more adequate interpretation of the brain connectivity and a much lower information loss. The task of connectivity-driven parcellation aims at regrouping vertices on the cortical surface that have very similar or correlated connectivity profiles towards the rest of the brain. The method we propose here for this task is to use an iterative multi-resolution Markov random field model for the task of parcellation, which is robust to initialization and noise, memory efficient, and highly parallelizable. It also yields very promising quantitative and qualitative results. The method goes as follows. We initialized our method with a downsampled mesh and a random parcellation on the cortical surface. The first stage is to update the parcel centers, which is done by selecting as a center the node that has the highest correlation with the rest of the nodes in the parcel. We then update our parcellation using a POTS model, where the main objective is to maximize the correlation of a node to its parcel center subject to smoothness constraints. If the parcellation has been strongly updated from the previous iteration, we keep iterating until the parcellation has converged. Once this is obtained, we increase the mesh resolution and iterate again until we reach the maximal resolution, which yields the output parcellation. We carried experiment on 25 preprocessed subjects of the Human Connectome project, all of which have been initialized using 15 Poisson disk sampling random initializations. We evaluate our method quantitatively by comparing two anatomical, random, hierarchical clustering, and spectral clustering parcellations. We obtain statistically significant improvement of the parcel homogeneity and information loss for most label configurations. Here is an example on how the parcellation evolves from a random initialization through 4 resolution levels. The method also shows a very good robustness with respect to initialization. We obtain an increase of almost 20% with respect to random initialization in terms of overlap. Qualitatively, we can observe that our parcel boundaries seem to match strong variation in myelination, as well as the boundary of Brodmann areas, especially in the motor area. To conclude, we propose an iterative and multi-resolution continuous POTS model with a smart center update based on the current parcellation configuration, a parcellation update based on the correlation between a node and its center. Our method is memory efficient, parallelizable, robust to initialization. In terms of result, it agrees with strong variation of myelinations and leads very promising quantitative results. Thank you for your attention.